Hello, my name is Amari Hitson, and I'm going to present to you the final lab of the semester entitled Create Your Own Adventure. The objective of my lab was to observe a paper ball tossed from one person to another, then create a computer model that predicts the motion of that ball. In a previous lab, I conducted a similar experiment with a paper ball in freefall motion. The object was similar, however, the ball moved in only the negative y direction. In this experiment, our system, the paper ball, moves in the x and y directions. While this may appear to be complex motion, you will find that many of the same basic principles apply to modeling this motion as well. The intent of the lab is to model the motion of a thrown object, detailing the components needed to do so. Finally, I will identify areas of improvement which could make the model more accurate. Following the lab, I'd like to answer these three questions. What components describe the motion of the paper ball? Which of these components can vastly improve the accuracy of the model? And what if more initial force was applied? How would the results change? As previously mentioned, many of the basic principles involved in single-axis motion apply to this observation. Firstly, it will be important to note Newton's first law of motion. An object at rest will stay at rest, while an object in motion will stay in motion unless acted upon by an outside force. For us, this will help us to model the velocity changes in both the x and y directions. Lastly, we will utilize Newton's second law of motion, which states that the force of an object is directly proportional to the magnitude of that net force and inversely proportional to the mass of the object. In our model, we observe the ball just after release. In other words, there are no forces acting on the object along the x-axis. We thus focus our attention on the y components of force, both the drag and gravity. Utilizing Newton's second law, we will see that the y-component velocity changes during the ball's parabolic travel. Because we see a change in the velocity, we know that the net force cannot be equal to zero. Thus, we calculate the force of gravity using the mass times the gravitational acceleration constant. We calculate the drag using the equation shown on the slide. However, for our purposes, we can simplify the first portion of the equation as a constant b, bringing us to our equation negative b times the velocity squared. As previously articulated, we see here that the x velocity remains constant, while the y-axis velocity changes, further affirming our investigation into the y-axis motion. To make our computational model, we start by putting in our initial conditions: the ball's mass, 4.8 grams, the gravitational acceleration constant, and the initial velocity and position. The initial velocity was found by calculating the velocity using the first two position vectors. The b constant was found by estimating using trial and error. To update the velocity, we utilize a derivation of Newton's second law. That is, the final velocity is equal to the initial velocity plus the net force over the mass times the change in time. To update the position, we utilize the previously calculated velocity using the final position is going to be equal to the initial position plus that last velocity that we calculated times the change in time. Finally, we distinguish the net force using our knowledge that the net force is equal to the force of gravity plus the force of drag, which we previously elaborated. The values of these equations are shown in the bottom right-hand corner of the slide. The model produced the shown diagram and position versus time plot. Comparing this to our observed model, we see a pretty large discrepancy from the observed model. Despite several attempts to distinguish a better B constant for drag, it was found that the peak position and final position could not be accurately aligned using the distinguished parameters. Future experimentation would greatly reduce this margin for error by obtaining a more accurate instantaneous initial velocity. We calculated our initial velocity by using the first two position points and the time difference between those two. By utilizing a smaller time step, we might be able to better predict the instantaneous initial velocity, thus improving our equation and our computer model. Finally, we arrive back at our initial question. What components describe the motion of the thrown object? Since we're only interested in the y-axis motion of this object, that distinguishes that the most important components are the force of drag and the force of gravity, as those both contribute to the net force and can be seen through the change in velocity along the y-axis motion of the object. Next, which of the components can vastly improve the accuracy of the model? As previously mentioned, a more accurate instantaneous initial velocity would greatly improve the model. Ours was calculated using the shown equation, but by decreasing the time step, a more accurate number for the instantaneous initial velocity can be obtained. And finally, what if more initial force was applied before the observation? How would the results change? Using all of the knowledge that we've discussed in this presentation, we know that the b constant would remain the same as the object is still the same, but the peak of the parabola would change, the velocities in both the x and y values would change, and the final position would vary. However, the methodology to model the motion would likely remain the same. So, to summarize, we didn't accurately predict the motion of the ball with the computer model, but we could do so in future experimentation if we used a more accurate initial velocity, and if we initialized the experiment at the same y value as the final y value. Finally, we learned that the motion isn't all that complex, and it's actually made up of the x direction net force, which is equal to 0, and the y direction net force, which is composed of the drag force and gravity force. Thanks so much for watching, and have a great summer.